Hello, this is a presentation of our paper, Latent Vector Recovery of Audio GANs with Applications in Deepfake Audio Detection. My name is Nicky Bayat. My co-authors are Vahid, Reza, Khazaie, Andrew Keys, and Yalda Mohsenzadeh. Let's first go over an overview of GANs. Generative Adversarial Networks, or in short GANs, are frameworks for training generative models. A GAN consists of two networks, a generator and a discriminator. The generator tries to generate realistic samples, while the discriminator tries to decide whether the given sample is real or fake. The min-max gain between the generator and the discriminator will help them both to enhance their respective performances. After training, we can randomly sample a latent vector and feed this to a pre-trained generator. Then the generator is capable of generating a realistic sample that is similar to the training data. For example, if the generator was trained on audio, then it will be able to synthesize an audio. For example, 0. The digit 0 in this audio was produced by a GAN. The problem of going backwards describes the scenario that we have an audio and we would convert it to a spectrogram, and we would like to fit this audio to an inverse mapping model. And this model will then be able to predict a latent vector. This predicted latent vector could then be fed to a pre-trained generator to reconstruct the target. The goal is to have the reconstructed audio as identical as possible to the input. Wavegen is a machine learning algorithm which learns to generate raw audio waveforms. In this paper, we use Wavegen trained on SC09 dataset of spoken digits. Our methodology for training an inverse mapping model is described in this figure, and it consists of two branches. The upper branch gets generated audio or fake audio as input, feeds this audio to an inverse mapping model, which is a resonant 18 based architecture, and this model will predict a latent vector. The loss between this predicted latent vector and the ground truth latent vector for these fake audios, which we call it the z-loss, will help to train the inverse mapping model. In addition, we would feed this predicted latent vector to a pre-trained Wavegen, and we would reconstruct the audio. And then this reconstructed audio also will be fed to a pre-trained digit classifier. And the loss between the features extracted from this network for the reconstructed audio as well as the generated input audio will give us a multi-level feature loss. The pre-trained digit classifier is a resonant 18 network trained on SC09 dataset with 95.41 accuracy. In the lower branch, we train the inverse mapping model on real audio. In this case, we do not have a ground truth latent vector, and therefore we cannot compute the z-loss. Hence, we will only compute the multi-level feature loss for the lower branch. So we will train the inverse mapping model one batch on generated audio and the next batch on real audio. In this slide, you will see some examples of our model predicted latent vectors and how it is capable of reconstructing the input audio. For example, for the fake audio digit 0, our inverse mapping model is able to reconstruct it. 0. And we would also compare our results with reconstruction using gradient descent here. 0. So in this case, Both methods are able to reconstruct the given audio. However, our method is an autoencoder based architecture, while in gradient descent methods, they will start with a random latent vector and they will compute the loss between the reconstructed and the target audio, and they use that loss to update the latent vector for many iterations until the loss is below a certain threshold. And obviously, this is more time consuming than autoencoder based approaches. In the second row, for digit 1, we reconstruct using our resonant 18 based inverse mapping model. And this is gradient descent. As you can see here, it can be seen in the waveform as well. The audio has a very low quality and it cannot be heard. In this slide, we'll show some quantitative comparison. So for a synthesized audio, the inception score is 7.23. So the higher the inception score, the better. And as you can see here, the reconstruction using gradient descent is 4.3, but our inverse mapping model has highest inception score compared to gradient descent and hybrid methods. And in hybrid methods, we will predict an initial latent vector using an autoencoder and then improve that with a few further steps of gradient descent. In terms of FID, our inverse mapping model is best. For FID, the lower the better. And in terms of MSE and SSIM, MSE between the audios and SSIM between the spectrogram of audios, a hybrid method has the best performance. However, we should keep in mind that this could be due to the nature of the objective function in gradient descent based methods. And this slide will show our results for real audio. So the real audio is obtained from SC09 dataset.
0.
This is a digit 0 that is in fact a human voice, and we reconstructed using our model
0
and using gradient descent. Our model performance is significantly better in this case. And for digit 3,
3
the reconstruction using resonant 18
3
and using gradient descent.
3.
In terms of quantitative results, for inception score, our model is better for real audio. In terms of FID, our inverse mapping model has lowest FID. For MSE and SSIM, hybrid is best, but again, it could be due to the few further steps of gradient descent and the way the objective function of hybrid gradient descent would work, which is based on MSE. And we also added a fifth column for real audio. We used our digit classifier to see how good the audio would perform in a digit classification task. So the real audio has a performance of 95.41% accuracy. And in second place would be audio reconstructed using our inverse mapping model with 71% accuracy. And as you can see, our model is significantly better than the other two in digit classification task. We also observed that recovering a latent vector from a fake audio is a much simpler problem than recovering audio from real audio. And the reason for that is because for fake audio, we have the ground truth latent vector, and therefore we are able to compute the z-loss. And we decided to conduct another experiment to see if this observation could be used in deepfake audio detection. We randomly sampled 100 audios from SC09 dataset. This is our dataset of real audio. And also, we sampled 100 fake audios generated by Wavegen, which would be our dataset of fake audios. And we trained two binary classifiers. The first one is trained to distinguish between real and fake spectrograms. The second binary classifier is trained to differentiate between recovered latent vectors of fake and real audio. We visualize our results using TSNE method. So you can see here, if we train the classifier on spectrograms, they're all very close to each other and it's not possible to differentiate between real and fake audio. However, if we train the classifier on predicted latent vectors, then you can see here that the red dots are real audio and the blue dots are fake audio, and we can easily separate them. This can also be seen in our table that we record the accuracy. So we trained both logistic regression and SVM, and you can see that the accuracy for predicted latent vectors is significantly higher than spectrograms in both cases. In conclusion, we propose a fast latent vector recovery method for both fake and real audio. We introduced the Z-loss to train our resonant 18 inverse mapping model. Further, we improved the model by adding a multi-level feature loss term to the objective function. We also conducted an experiment that proves inverse mapping of audio GANs can be used in deepfake audio detection. Thank you for being here today.